Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like Moore's law, pipelining, superclarity, SIMD. Let's get started. Slide 1. Moore's law. Moore's law is a fundamental principle that has shaped modern computing. It was introduced by Gordon Moore, co-founder of Intel, in 1965. He observed that the number of transistors on a microchip doubles approximately every 2 years, leading to significant improvements in processing power, efficiency, and miniaturization. This trend has continued for decades, driving innovations in processors, AI, and cloud computing. Key implications of Moore's law. 1. Increased processing power. More transistors mean higher computational capabilities. Each new generation of processors becomes significantly faster than its predecessors. Example: modern CPUs like Intel's 13th gen processors handle billions of instructions per second. 2. Miniaturization. As transistors become smaller, devices become more compact and portable. Smartphones today are more powerful than early supercomputers. 3. Lower costs. Mass production of smaller transistors reduces chip manufacturing costs. This makes high-performance computing more affordable. 4. Higher energy efficiency. Newer chips consume less power per operation, extending battery life in portable devices. Example: Apple's M1 and M2 chips prioritize efficiency while maintaining high performance. 5. Rise of AI and cloud computing. The exponential growth in processing power supports deep learning models, cloud platforms, and data-intensive applications. Example: Google's tensor processing units (TPUs) handle AI computations at high speed. 6. Limitations. Emerging transistors cannot shrink indefinitely due to quantum mechanical effects. The heat generated at such small scales affects efficiency and reliability. 7. Alternative technologies. Researchers are working on quantum computing, neuromorphic chips, and 3D transistor stacking to push beyond Moore's law. Example: in 1971, Intel's 4004 processor had only 2300 transistors. Today, chips like the Apple M2 have tens of billions of transistors, offering incredible performance. Significance. Moore's law has been the driving force behind technological advancements, enabling faster, smaller, and more efficient computing devices. However, as physical limits approach, new computing paradigms are emerging. Slide 2. Challenges to Moore's law. While Moore's law has successfully predicted the growth of processing power for decades, it is now facing significant challenges. As transistors become smaller, manufacturing, power consumption, and heat dissipation become major obstacles. Challenges. 1. Physical limits of transistors. Transistors cannot be infinitely reduced in size due to quantum tunneling effects. The industry is approaching the 1 nanometer threshold, where electron leakage becomes problematic. 2. Power and heat constraints. The smaller the transistor, the more heat is generated. Efficient cooling methods must be developed to sustain performance. 3. Manufacturing complexity. Extreme ultraviolet lithography (EUV) is required to fabricate modern chips, making production more expensive. Only a few companies, such as TSMC, Intel, and Samsung, can afford the advanced technology required. 4. Rise of quantum computing. Instead of traditional transistors, quantum computers use qubits to perform computations exponentially faster. Companies like IBM and Google are leading in quantum research. 5. Need for new materials. Silicon-based transistors may soon reach their limit. Research is exploring graphene, carbon nanotubes, and photonic computing as alternatives. 6. Economic barriers. R&D costs for new semiconductor technology are skyrocketing. This may limit smaller companies from entering the high-performance computing market. 7. End of Moore's law. Some experts believe that Moore's law will slow down and eventually become obsolete within the next decade. The focus is shifting toward performance per watt efficiency rather than pure transistor density. Example: IBM's 2 nanometers chip technology claims to extend Moore's law with new fabrication methods, offering higher efficiency in performance. Significance: overcoming these challenges requires alternative computing technologies such as quantum computing, neuromorphic chips, and photonic processors. The future of high-performance computing will depend on innovations beyond silicon-based transistors. Slide 3. Introduction to pipelining. Pipelining is a key technique in modern CPU architecture that improves processing efficiency by executing multiple instructions simultaneously. Instead of completing one instruction before starting another, the processor overlaps different instruction stages. How pipelining works. 1. Instruction fetch (IF). The processor retrieves the next instruction from memory. 2. Instruction decode (ID) determines what operation the instruction performs and which registers are needed. 3. Execute (EX). The arithmetic or logical operation is performed on the data. 4. Memory access (MEM). If needed, data is retrieved from or stored in memory. 5. Write back (WB). The final result is stored in registers for further use. Example: without pipelining, the processor completes one instruction before starting the next, resulting in slow execution. With pipelining, the processor overlaps execution, leading to higher efficiency. Significance: pipelining increases CPU instruction throughput, allowing modern processors to handle multiple operations efficiently, especially in AI, gaming, and high-performance computing. Slide 4. Pipelining versus non-pipelining. When we talk about CPU performance, one of the key factors is how efficiently instructions are executed. Pipelining is a technique that allows multiple instructions to be processed simultaneously by breaking down execution into smaller stages. In contrast, non-pipelined processors handle one instruction at a time, leading to slower execution. Key differences explained. 1. Execution speed. Pipelining accelerates performance because multiple instructions are being processed at the same time. Non-pipelined CPUs must wait for each instruction to complete before starting the next one. 2. Efficiency. In a pipelined CPU, every part of the processor is actively working on different instruction stages. Non-pipelined CPUs have idle units when waiting for instructions to complete. 3. Complexity. Pipelining requires advanced logic to manage overlapping instructions. Non-pipelined designs are simpler, but at the cost of lower performance. 4. Instruction throughput. More instructions per second can be completed with pipelining, making it ideal for performance-driven applications. Non-pipelined processors handle fewer instructions at a time, limiting their efficiency. 5. Use cases. Modern processors like Intel, AMD, and ARM chips use pipelining to improve processing speed. Non-pipelined architectures are used in basic microcontrollers and low-power embedded systems where simplicity is prioritized. Example: a modern gaming processor like AMD Ryzen 9 uses deep pipelining to execute multiple instructions simultaneously, making games run smoothly. A simple microcontroller in a washing machine uses a non-pipelined architecture because it doesn't need high-speed computation. Key takeaway: pipelining is a major advancement in CPU design, allowing modern processors to achieve high efficiency, better speed, and improved multitasking. It is essential in applications like AI, cloud computing, and high-performance gaming. Slide 5. Superscalar processing. In modern computing, simply increasing clock speed is not enough to improve processor performance. Instead, superscalar processing allows a processor to execute multiple instructions in a single clock cycle by using multiple execution units. This significantly boosts speed and efficiency, making it ideal for multi-threaded applications like AI, gaming, and cloud computing. Key features of superscalar processing. 1. Parallel execution. Unlike traditional CPUs, which process one instruction per cycle, superscalar processors execute multiple instructions simultaneously. 2. Multiple pipelines. Instead of using a single pipeline, multiple functional units, such as ALUs and FPUs, work in parallel, handling different instructions at the same time. 3. Dynamic instruction scheduling. The CPU reorders instructions for maximum efficiency, ensuring that execution units are never idle. 4. Register renaming resolves data dependency issues by dynamically assigning registers, preventing execution stalls. 5. Branch prediction. Anticipates the next set of instructions, reducing pipeline stalls and increasing throughput. Example: Intel Core i9 and AMD Ryzen 9 processors use superscalar architectures to boost multitasking and gaming performance. Significance: superscalar processing is essential in modern CPUs, as it allows for faster, more efficient execution of instructions, improving performance in areas like big data processing, AI, and high-performance computing. Slide 6. SIMD, Single Instruction, Multiple Data. Parallel computing plays a key role in accelerating performance-intensive tasks. SIMD, Single Instruction, Multiple Data, is a processing technique where one instruction is applied to multiple data points simultaneously, improving parallelism and efficiency. How SIMD works. Instead of processing one data element at a time, SIMD applies the same operation to a set of data elements simultaneously. This is particularly useful for tasks that involve large volumes of repetitive calculations, such as graphics rendering, AI computations, and physics simulations. Example: vector processors in GPUs use SIMD for faster image processing, AI computations, and machine learning models. Significance: SIMD allows for faster execution, reduced latency, and increased computational throughput, making it crucial for applications that require real-time data processing. Slide 7. SIMD versus MIMD, Multiple Instruction, Multiple Data. Key differences explained. 1. Execution type: SIMD processes the same operation across multiple data points simultaneously. MIMD allows different processing units to execute separate instructions on different data sets. 2. Parallelism: SIMD excels in tasks with repetitive operations, while MIMD handles more complex, multi-threaded computations. 3. Use cases: SIMD is used in image processing, AI, and gaming. MIMD is used in cloud computing, database management, and supercomputing. Key takeaway: SIMD is optimized for highly repetitive tasks, while MIMD is better suited for diverse, multi-threaded workloads. Slide 8. Applications of SIMD in high-performance computing. SIMD is widely used in scientific computing, AI, and real-time applications that require fast, large-scale data processing. Key applications of SIMD. 1. Image and video processing. Gaming consoles, video editing software, and 3D rendering engines use SIMD to enhance rendering speed and real-time effects. 2. Artificial intelligence, AI, and machine learning. Deep learning models leverage SIMD to process large AI datasets efficiently. 3. Physics simulations. Used in weather modeling, aerodynamics, and material science simulations. 4. Cryptography. Accelerates encryption and decryption processes, ensuring faster cybersecurity protocols. 5. Financial modeling. Enables high-frequency stock trading calculations and real-time risk analysis. 6. Weather forecasting. Processes large climate data sets in parallel, providing faster predictions. 7. Bioinformatics and genomic sequencing. SIMD speeds up DNA sequencing and drug discovery by processing genetic data in parallel. Example: NVIDIA Tensor Cores leverage SIMD to enable AI-powered real-time image processing. Significance: SIMD is crucial for real-time processing, AI computations, and scientific research, offering massive improvements in efficiency and speed.